Our presentation today features the precast segmental bridges on the Louisiana Department of Transportation and Development's I-49, I-220 interchange. We thank Greg Freeby, Executive Director of the American Segmental Bridge Institute, for coordinating this presentation. We're pleased to welcome our presenters, Paul Vaught, Assistant State Design Administrator with the Louisiana Department of Transportation and Development, Craig Finley, Managing Principal of Finley Engineering Group, Inc., and Ivan Liu, Bridge Engineer with Finley Engineering Group, Inc. Paul?
Thank you for the introduction, Mary Lou. I'd like to thank everyone for joining the webinar today. I hope that this project example can provide some beneficial information. As was said, my name is Paul Vaught. I'm one of several assistant administrators in the bridge design section at the Louisiana DOTD. I'll be providing a project introduction and overview. Then I'll turn it over to Craig Finley, the managing principal at Finley Engineering Group, who will talk through some of the design and construction specifics of the precast segmental superstructures. Ivan Liu was supposed to be co-presenting with Craig, but he had a scheduling conflict, so Craig will cover those portions of the presentation as well. I started to make the project participant slide and realized that there were too many to fit on just one slide. So here are the participants on the design development side of the work. I'd like to specifically highlight TRC, who was the prime bridge consultant for the project, and Finley, who was brought onto the project when the precast concrete segmental bridge alternative was added. I'd also like to note that all of the geotechnical design work was done in-house by DOTD. Here are the participants on the construction side of things. PCL Construction was the low bidder and prime contractor for the project. Some of their key subcontractors are listed on the right. The construction inspection participants are listed on the left. DOTD's in-house staff led the construction inspection effort and was supplemented by staff from Beast Engineering. FIG served in an advisory capacity and provided DOTD with some specialty knowledge relative to precast concrete segmental construction. The project is located in Shreveport, Louisiana, which is in the northwest corner of the state. There are 3 interstate routes in Shreveport. I-20 runs east-west through the city. I-220 is a northern bypass which connects to I-20 on either side of the metropolitan area. And I-49 approaches Shreveport from the south, co-locates with I-20 and then I-220, then continues from Shreveport to the north. Speaking of Interstate 49, this project is part of a greater overall effort to connect Lafayette, Louisiana to Kansas City, Missouri, where it will tie into the southern terminus of Interstate 29, which in turn runs all the way north to Canada. DOTD has referred to the portion of I-49, which is shown as the star on the map, as I-49 North. That corridor runs from Shreveport to the Arkansas state line and was subdivided into 13 design and construction projects. Altogether, the 13 projects built over 36 miles of new interstate and cost approximately $570 million. The project we are discussing today was the southernmost and was the final component of I-49 North, Segment K. Incidentally, there's also an ongoing effort by DOTD to upgrade the existing US 90 to interstate standards. When completed, this would extend I-49 south from Lafayette to New Orleans. This is an aerial and layout of what was proposed Segment K. North is to the right. I-220 runs from the top left to the bottom right of the screen, and I-49 begins with an I-220 interchange in the middle of the picture and then runs north. You'll note the interesting geometry for the interchange. This project had a number of challenging site constraints, including an active landfill to the south, an environmental justice neighborhood to the west, and a 4F property to the east. Due to time and funding demands, the project was split into 2 phases during final plan development. The interchange with Martin Luther King Jr. Drive was separated out and let in phase 1, and the interchange itself, along with some I-220 improvements, was let in phase 2, which is the project we'll be discussing today. Phase 2 consisted of widening of 2 existing parallel steel plate girder bridges over Russell Road, which we won't be covering, and constructing 3 flyover ramps serving as direct connectors between I-220 and I-49, which are the subject of today's webinar. Ramp EN, or east to north, which is a 2-lane ramp over 3,000 feet in length, has a width that varies from 64 to 40 feet, which was due to a gore area at the beginning of the structure, and has a radius of 3,500 feet. Ramp SE, or south to east, which is a 1-lane ramp that is 3,300 feet long and has a width of 33 feet and a radius of 840 feet. And ramp WN, or west to north, which is a 1-lane ramp that is 700 feet long, has a width of 29 feet and a radius of 5,500 feet. All 3 ramps are founded on drilled shaft supported footings. Typically, footings at intermediate bents had either 9 or 12 66-inch diameter drilled shafts that were, on average, approximately 60 feet in length. The majority of the substructure consisted of single column bents with flared caps, but due to the severity of the skew crossing of ramp EN over I-220, 2 straddle bents and 1 cantilever bent became necessary. The straddle bents were post-tensioned, but the cantilever bent was conventionally reinforced. We were required to maintain 1 lane of traffic in each direction for the duration of the project. The original suggested sequence of construction proposed closing the median lane on each side of the interstate to facilitate the median construction work, and closing the outside lane on each side to facilitate the outside work near the shoulders. However, during construction, the DOTD project construction team, in conjunction with the contractor, devised the scheme shown, which was to cross over traffic and completely close one side of the interstate at a time. This change greatly simplified the construction and increased safety by moving the traveling public farther from the construction work. You'll note in the picture on the right that the temporary support tower for the superstructure near the straddle bent is positioned in the middle of what would have been westbound I-220. This was a design bid build project. The DOTD administration at the time decided to include bid alternatives, but because precast segmental concrete was a new technology to the state, the belief was that providing a more conventional design alternative in the form of steel trapezoidal box girders would provide a baseline alternative, mitigate our risk, increase the number of bidders for the project, and ultimately ensure that we achieve the best possible value for the project. There was obviously additional cost associated with the alternative, but unfortunately for our design consultant, given the funding constraints, there wasn't much additional time provided. However, ultimately our designers met the required letting schedule and we received 4 bids on the project. 3 bids, including the low bid, were received for the precast segmental alternative, and 1 bid was received on the steel trapezoidal box alternative. Lastly, I'd like to note that this project recently won the Regional AASHTO Award for Best Use of Technology and Innovation. This is a photograph of our secretary, Dr. Sean Wilson, receiving the award at SASHTO last month. And I actually just found out this past Monday that this project also won the 2019 ASBE Award of Excellence, which will be presented at the 2019 ASBE Conference this November in Orlando, Florida. Like with any project, this project was challenging during design development and construction, but it's nice to see not only the final product functioning as was intended, but also for everyone to be recognized formally for all of their collective efforts. So with that being said, at this time, I'd like to turn the presentation over to Craig to discuss the more technical aspects of the project.
Thank you, Paul. Here's the agenda of what the major topics that I'm going to discuss with you today, and in some detail on it. Before I begin the presentation, I'd really like to stress a key point and something I think is very important to understand with these style of bridges. The segmental bridges are a construction technique that has design implications, and as we walk through these slides, I think it'll be apparent why I believe strongly in this. Another point and topic on this talk, it's going to be a focus on the applicability of ABC construction principles, and we'll go into detail on several items for that. And I think most of all, we're going to share a very successful precast segmental bridge project and give you a few what I'll call tricks of the trade. As Paul shared with you, probably the biggest challenge on this project at the beginning is the desire by LaDOTD to introduce precast segmental bridge construction into their project type. So with that said, this job from day one was a cost competitive option presented for the contractors, and that drove a lot of our thinking and a lot of the challenges to really develop a fine-tuned project that had the design incorporating details that we knew was important for a successful project. And again, like most projects that have an A, B, C component to them, price is always a decider. The LaDOTD had worked a lot with the local stakeholders, and there was a demand for some project aesthetics. But again, in a cost competitive environment, these needed to be low cost or no cost. So some of the things that were developed and added to the project were the column cap details, which serve a multitude of purposes we'll talk about later in both construction and future maintenance. But it also does a good job of visually transitioning between a constant cross-section column into a variable depth superstructure. The local stakeholders wanted something unique about this project that kind of addressed their social and cultural significance in the area, and there was a precast medallion that was developed in conjunction with that kind of spotlights some of the influences. The consistent visual of the haunch segments of varying span lengths was very important, and when you look at this picture, it's obvious to see that the linear haunch on the first 5 segments was a critical design aspect on the project. Columns were constant shape, but we incorporated rustifications and bevels in it to give it a little more interesting look. In the end, I think the job has very good aesthetics, and they're basically things that are no cost, but were incorporated in to meet the project challenges at the beginning. With this project, one of the biggest challenges, Paul shared some of the details, but probably the biggest challenge is this project has 730 segments on it. But with that, in those 730 segments, we had to adapt to span lengths of 140 to 260 feet. The depths of segments ranged from 9 to 13 feet. We had a lot of variation in the height of the columns. But probably one of the 2 biggest challenges on this project were how to handle the varying roadway widths, which are very significant, you can see there, but also the various curvatures. This right here that we're going to show, these challenges are perfectly suited for ABC construction principles, and really drives the means and methods on this project that made it successful. The big challenge is, how do we cast 730 segments with the minimum number of casting machines? A casting machine typically costs approximately $500,000, and they're good for 500 to 600 segments before refurbishing. With the small number of segments and a lot of variation, both in depth and width and cross fall in the segments, we had to come up with a shape in the design process that allowed consistency and could be adaptable with constant forms and different insert panels. You can see on the left a typical segment there in the casting machines that have the stack to adjust for the vertical dimensions of the segment. And in the right, it's again a typical segment, but form panels were introduced into the core forms for a deviation segment. Critical element always in a project is segment geometry, and these casting machines, one machine could accommodate all the variances. In a project, it's always a major cost component of where you're going to cast the segments. It was no different than I-49, I-220. There was some adjacent property within the right-of-way that was available, very close to the interchange that the casting yard was set up in. Other locations had been investigated, but this provides the most efficient use of labor, management, and also reduces transportation costs. The variance in the pier heights and span lengths had to be accommodated in a uniform fashion and with a consistent set of equipment and forms to make it feasible. Overall, the erection methods drove our thinking in the preparation of the design. Faster and more for less were key components of making this a successful project. Here's a view of the casting yard, fairly typical of what a precast segment casting yard. In the upper left, the gray casting machines are shown. The core forms are retracted, and at the rebar jigs allow for a linear application into it. And in the right side, you can see some of the form inserts and the rebar cages that are going to be tied. The casting yard was about a half a mile from the site, and the storage was adjacent to the casting yard. This was a very efficient layout and very typical of what you would see in a precast match cast operation. Casting started at the pier segments and went out to the cantilevers, as you would expect for balanced cantilever construction. On the columns, again, we've talked a little bit about the aesthetics, but what we wanted to do is simplify the forming. So we had a column, or we had cross-section details that had the consistent column shape, even though within the column the reinforcing patterns were varying, but the shape was the same and the caps were the same. The variable pier heights just were accommodated by the contractor's forming system and the number of pours per column. Everything was mildly reinforced and provided a simple and conventional construction process. Again, for the use of these details, both a competitive on first pricing was a premier consideration, but also future maintenance of how bearings could be replaced, drainage, and the aesthetics had to be low cost, no cost. In the substructure, we used drilled shafts, 66-inch, with some fairly high loads. This gave compact footings, but what really the advantage of it was is the project was designed to allow the temporary shoring towers used to stabilize the cantilevers during construction to rest over drilled shafts and within the footings. This ability to do this minimized the amount of secondary or additional foundations in the project and simplified, streamlined construction. So again, this, even though it's not something to speed construction, this is a very important detail to understand on how you match your construction methods with the design. For superstructure construction, modular stability towers were used. These were approximately 12 feet sections and could be stacked for between the shorter columns of approximately 14 feet up to the 90-foot height. At the base of the column on the footing was shim stacks that allowed variation, and at the top of the column there was small pieces that could be added in jack heights to accommodate the height. As you can see on this, access on the site was really good. Ground based cranes were used, and the access towers allowed the cranes to get in close to lift the segments that, again, minimize the craneage and the cost for what these were to lift about a 90-ton segment. Balanced cantilever construction, one of the biggest pros of this style of erection method is it's not linear. You could work on multiple locations. The design impact comes on the closure, but it allows the project to be accelerated versus a span-by-span style that's very linear. Segments were pre-positioned for the crane erection, which allowed the erection of the deck to go as quick as possible in the work days. So overall, this sequence that was developed in the design documents provided a faster, simpler, and a very, very competitive erection method with not high or unusual equipment demands. This is probably the biggest challenge at the beginning of the project. You can see the various ramps and what the roadway widths are, and you can see what is happening on the structure depths. When we set up the cross sections on this, we wanted to take as much variation out of the segments in the wings by being able to add to the casting cells temporary bulkheads that could be shortened up on the transverse width of the segment. This carried through to WN, where the temporary bulkheads had to be able to come into the thickened side of the segments. It worked very, very well, gave us a tremendous amount of flexibility, and was an easy detail to develop. Again, the casting machines could accommodate all of these changes in the machine design, even though they had multiple casting machines. Here is a picture where you can see on the left a good example of how the form panels were used on a typical segment on it to get the interior shapes that may be different for, say, a pier segment, a abutment segment, or a deviation segment, where it was done inside the segment and inside the core forms. On the right, you can see a fairly simple rebar cage that's coming out of the jigs, and where we adjusted for depth was in the webs, the height of the bars, and also transversely when the segments narrowed, we adjusted in the length of the wing bars. Here's a picture of a pier segment. So again, you can get a good idea of how form panels were used for the cores of the varying segments, but still with the same core forms. And on the right is a very good example of a simplified longitudinal PT layout and transverse PT with it in the segment details. The bulkheads on these projects were very important to allow the transitioning of the tendons as they move across the slab, but also this project uses a lot of external PT with the diablos, and there's varying heights and angles that have to be accommodated. So overall, you can see that the details are fairly simple and are extremely flexible to adapt to the varying conditions on the project side. Here's an example of the cantilever tendon, top slab tendons in a cantilever. It's a good example of how the tendons are deviated into the ducts that are in the top slab. On this project, the cantilever tendons are all internal to it. The blocks that you see there under the red longitudinal tendons in the elevation were where the temporary PT bars were anchored for segment erection. Here's what it looks like, and as you see, there were one longitudinal post-tensioning anchor per web per segment, and where you can see the red circles, this is where the ducts move, so they anchor at the web top slab intersection, and as they progressed out, the tendons would move out into the holes and then come back in. Here's what the positive moment continuity PT layouts look like. These are all external tendons. They're grouted. but the only bond on the tenon comes in the pier segments with it. So these are totally external. You can see that these tenons deviated both horizontally and deviated vertically through the course of this, and also this is a simple illustration, but if the horizontal geometry was shown, there would be horizontal deviations due to the deck geometry in this too. One advantage of this type of positive moment continuity is the inclined tenons that reduce the shear requirements which in the segments, which also reduces the thickness of the webs. And with the tenons being external, it reduces the dimensions required in the bottom soffits for tenons to be uniform. This style of PT typically shows about a 10% reduction over conventional internal PT, but it also lightens the segments and things, and it's much easier to inspect and maintain in the future. So our experience is this is a significant time saver and a very good cost savings approach. Here's where they look. The red dots show where they deviate. The darker rectangles are shown for anchors. So the tendons are anchored in the pier segments, and based on the tendon layout, some can be anchored in the deviation saddles or the deviators, which gives us some overlap. It's a little more efficient and flexibility in how the PT is installed. With it, you can see that, as I discussed on the previous slide, the eccentricity of the tendons are a little higher due to them being outside of the bottom slab, but the bottom slab is narrower. Here's what it looks like during construction. You can see the grout on the photo on the right. The tubes coming out are the grout tubes. The grout caps are on the tendons. They're ready for grouting. The ducts are PE pipe. There's no Schedule 40 pipe in any of the deviations in the deviators, abutment segments, or the pier segments. The duct runs continuous through the deviation points. So this is a good example of the differences, say, over conventional internal tendons. I think with this project is conventionally grouted. Some of our current projects now are featuring the continuity PT that has a wax in it. They're unbonded, but with a wax versus a grouted, and that's showing a lot of promise for a little easier, faster installation, but also some advantages for long-term maintenance. Everybody that hasn't used Diablos 4 always asks, how do you do it? It's really a very, very simple approach. You can see the white, it's spun nylon. There's two pieces to it. It has a threaded rod through it that attaches to the form panels to hold them into position. And with Diablos, one size fits all. So the bell shaped at the end of the Diablos is sized to fit the vertical and horizontal deviations of the tendons, and to be at the point that you never have a tendon bearing on the edge of the deviation or the Diablo. These easily fit in the rebar cages, and the the taper on the Diablos makes it easy to pull them for the draft and leaves the formed area. Here is an illustration that kind of shows a little more of the detail. The yellow portions there are what the Diablo looks like. So you can see on the, the yellow is what the Diablo looks like. So you can see the one size fits all. It handles the angle deviation both vertically and horizontally. And as they move through, the ducts are continuous through the deviation or to the anchorage. This makes it a lot easier. This makes it a lot easier for installation, that the couplers that you can see there can vary anywhere along the length based on a contractor's how he wants to handle the duct materials. Here you can see kind of the basic premise on how a Diablo works compared to Schedule 40 pipe and a deviation saddle. On the left, you can see the basic design requirements are the tendon and ducts have to bear on the curved portion of the Diablo, and a deviation saddle with pipe, you account for the strand bearing on the pipe, which then bears on the concrete. Diablos, when we first brought them to the U.S., we did some testing over 1 million cycles. The owner was concerned about the potential of strand burn or duct burn by installing the strand or during the post-tensioning operation. With over 1 million cycles, there was no issue of duct burn on that. It's very successful. One of the issues with standard 40 pipe is it requires very, very high tolerances of placement, and putting them in a casting machine makes it very difficult that this placement is both vertically, horizontally in the machines, and it's down typically to a quarter of a degree. So I've been doing this almost 40 years, and if I ever have a project where the deviation pipe is perfectly placed in a deviation block, it's probably a classic example of better lucky than good. So the Diablos take that tolerance issue out of the equation. Also, a Diablo style system has less losses due to friction in the deviation pipes, and there's virtually no strand break in a Diablo, where pulling a longitudinal tendon, it typically has the tendency to trap some of the wires on the surface bearing against the pipe and has wire breakage. Here you can see in the layouts of what it typically looks like. It's a difficult couple between the steel pipe and the plastic PE pipe as far as what the straps look like and the neoprene sleeve that goes over it. You can see it's very similar between the two, except your plastic on plastic versus pipe. Let's take a minute and talk about the number of segments on the project and how they're configured, just to get a better understanding of what the importance of having a common segment shape and how you handle the changes in some of the dimensional parts in the core of the segment. Pier segment, again, uses the standard shape, but it's got diaphragm panels in it to handle the diaphragm of the pier segment and the Diablos. Very similar on a deviator segment and an abutment segment. The variable depth, the bottom soffit of the forms moves up the webs, so it's narrower at the pier, wider as you move out, and that's an easy detail to handle with frames that sit into the bottom soffit tables. Key point and takeaway from this is maximum consistency of common details for the maximum number of segments, and try to minimize any, the number of, I'll call it the oddballs. So you can see from these things, 602 out of the 730 are virtually the same style, same details. Balance cantilever construction. The contractor that PCL was a contractor for this project and had recently finished up a similar project and had available all the temporary towers. So with that was really an advantage, I think, and can be seen in the difference of the pricing. Same support system was used between the tall and short piers by having a modular components that could be stacked. If you see on the top under the blue tarps, these are the jacks that will put the geometry into the segments for erection. A key feature of segmental construction is they're going to erect in the same position they were cast. So there's not an additional adjustment or fix at this point. Cranes, you can see one size crane was used. Multiple cranes were on the project, but everything was sized to balance the equipment requirements. And the same method or style of cantilever erection was used on all ramps, all for the segmental portion of the project. Again, probably the strongest thing I can say from an ABC construction techniques, balanced cantilever works fantastic and spans 180 to the 275 range. It's simple. It doesn't require a lot of temporary construction equipment. Segments being kept in a usable, readily available crane size. But I think, you know, the advantages that you can see are the 3 points before. Nonlinear construction sequence, which allows schedule acceleration, multiple locations at the same time, helps prevent a linear process that if there's a problem at one location, you're stopped until it's resolved. And the precasting of the segments off-site reduces the amount of time that construction is going on the site, and it just is good accelerated bridge construction that multiple activities will be going on at the same time frame. Some of the other details on the project that may be of interest, disc bearings were used. They were fairly highly loaded with it. The movements on this, we try to minimize the number of expansion joints. So these bearings accommodated up to 8 inches of total movement. The bearings were aligned to the center of stiffness of the bridge. And so it's just not horizontal, whatever. So again, it's important on long distances between expansion joints. The bearings need to follow the line of action. We use finger joints up to 10 inches in movement at the expansion device. And that was based on up to 1,900 feet between expansion joints. So again, finger joints give a good performance. And they're easy to maintain and inspect, and that was important to the owner. Drainage was conventional, scuppers on the cantilever wings, piping to the center of the box, and back to the center of the pier where it dropped into a catch basin at the columns. As any project, it's always important, and we always like to really say, hey, what's the lessons learned and what have we done? The I-49, I-220 project was fantastic from the point that it gave us a second chance to refine some details that we developed for the Palmetto Expressway. Similarities were in large interchange flyover ramps, veritable spans and cross sections. This was the first use of Diablos in the state of Florida, and it had tremendous success, which gave the Louisiana LaDOTD confidence that it was the right solution for this project too. Common segment details, we kind of put a little perfection and tune up on what was done on Palmetto, and again, similar casting and erection requirements. The big difference on Palmetto is the interchange was an existing interchange, and it was built with a launching gantry above the decks and over traffic, where I-49 and I-220 was a new interchange, and we could work for the ground. Again, similar aesthetic requirements and similar results. So this was really beneficial in the development process. It also gave Louisiana LaDOTD a chance to see what we were talking about before they added the precast segmental alternate to their bid documents. Another takeaway or lessons learned: experienced contractors with existing resources, whether they be people or they be equipment, are really important on the projects. Using variable depth segments for variable span length, especially getting up in that 265, 270 range, is really a good way to handle it versus getting a lot of segment depth. Diablos, I personally have the opinion Diablos are the only way to go for deviation, and external post-tensioning has tremendous advantage both in time, in cost, and future maintenance flexibilities. As any ABC, any segmental project, minimize the exceptions and maximize the commonality of the details and methods. Special equipment, try to keep it at the minimum that you can, and try to keep the methods that are repeatable. Balanced cantilever, I'm a big fan of balanced cantilever just because of the special of the advantages on it being able to work in multiple locations, being able to be a non-linear process either from a scheduling or a construction point of view. And I think the construction simplicity drives cost efficiency, and that's always important to everyone. So with that, ends our presentation, and I'll turn it over to you, Paul, for the Q&A.
All right. Okay. Thank you for the good presentation. At this point, we'll turn it to Paul Lives to moderate the question and answer period. Paul.
Okay. Thank you, Torrid and Craig. Really good, and Paul, very good. We do have a number of questions, about 12 or 13 that came in during the session, and we had 24 that came in before the session, so we'll go ahead and get it underway. We have broken them down into design questions, construction questions. There's one question on maintenance, and then on cost. So with that, we'll go ahead and get underway. The first one we had was a question about how would you really know if segmental construction is a better and cheaper option compared to other options in the bridge when you're in the bridge planning stage?
Paul, Vaught, do you want to answer that from an owner's perspective?
Sure, I'll take a stab at it. I guess the short answer is when we started this, we didn't know if it would be cheaper. And then throughout the process and learning, like Craig was discussing, basically it all gets down to how much you can make use of your casting machines. So minimizing the number of casting machines you're going to need. I think the rule of thumb I heard was somewhere around 300,000 square feet of bridge. But again, that all depends on how much of it is similar and how much of it is different. And on this project, Finley and TRC were able to have essentially the same casting machines be able to fabricate all of the structures.
Okay.
Maybe to add a little bit about it. ASB keeps a database of all the projects, and it has some good rule of thumb square footage costs that in a bridge development study are applicable, to take a look on that one. We felt like this project, even though it was smaller on number of segments and things, it had some definite opportunity and advantages for precast segmental. So that's how we approached it.
Okay. What were maybe some of the big structural design issues that you had in the project?
Probably the biggest thing was the horizontal and vertical geometry of the ramps and the span lengths. So that really added a complexity on how could we accommodate, let's say, a common segment shape over to varying cross slopes, varying span lengths, to accommodate that to not have too many one-offs or oddball pieces. So that was probably the biggest challenge initially.
Okay. So you've kind of mentioned the challenges. What about the radius? Did you consider that a big challenge?
We had done similar projects and radiuses down in the 250-foot range, so that didn't really present much challenge. I mean, we were used to using trapezoidal segments, and during the initial layouts, that was fairly easily accommodated.
Okay. Can you discuss maybe the structural design of the bridge with regard to load and resistance factor design, or maybe versus allowable stress design, and maybe some of the differences you would have?
Paul, do you want to answer that from Louisiana DOTD's specifications?
Sure. This bridge was designed in accordance with AASHTO LRFD. Louisiana has a load factor multiplier on top of HL93 due to some of our routine vehicle loads that are able to travel our roads. So from a design perspective, other than the fact that it was a different type of structure, all of the operational importance factors and redundancy factors were as they would be for any other project.
Okay. Can you discuss the analysis method used? And there was a question about, was it a 3D finite element, or really what kind of programs were used in the design?
For us, everything we do is 3D, time-dependent calculations. They've got finite element capabilities within the software. So, that's pretty standard, pretty routine. This project was run under Bentley's RM. It was checked with LARSA, and our current preferred software is Sophistic.
Okay. Was an alternative software, you said it was checked with LARSA, was there an alternative software used for checking purposes? I think you had some other consultants involved in maybe advising LaDOTD on the design, I guess.
TRC was the prime. We worked under DRC in the project. We laid out the segmentals. DRC did the detailed design on one of the ramps, and we were asked by Louisiana DOTD to do a back check on each other. RM was the software used for the design, and LARSA was used for the independent check of the other's work.
Okay. How did you decide to go with linear to constant haunches versus maybe a parabolic haunch?
On the Palmetto project, we had developed this idea for a couple of reasons. One, if you use constant depth and you're in this range of 270 feet, you'll get a segment depth, figure L over 22 just as an average. You'll get a segment depth that's hard to transport the segment under typical interstate clearance bridges. And with that 2.5, 3 feet for the hauler, the segment plus 2 feet, 10 inches of rebar sticking out for the barriers. So we've gone to doing the linear haunches. That'll give us a depth where we need it over the pier and the constant depth in the center portions of the project. Also, we standardized the number of haunch segments. On this project, it was 5, and the rest are constant depth. So it allows a visual on the bridge that I'll say balances, or it's easy to see what's being done with a structural that accommodates a big structural problem. And varying span lengths, if you're going to vary the depth, you're going to have different bottom soffit widths. You're going to have different shapes and different depths, where this puts a uniformity into whether it's a longer span or a shorter span.
Okay, there was a question that came in about the choice of the erection method in the balanced cantilever versus with all the room. That did you consider maybe building it on falsework the whole way?
We didn't consider falsework on any portion of the project, with the exception on ramp EN. There's a transition coming in, so the first span on it was on falsework. That it had a wide variance, and it was just the width at the abutment was too wide for the boxes, and it was only in one spot on the project. Using falsework, if this project was in, say, the West Coast, falsework and maybe have cast in place on falsework would maybe have a competitive option. In most of the U.S., people aren't accustomed to having that much falsework and building in that manner. So our experience was that precast segmental and balanced cantilever was going to be more cost effective and attract a bigger number of contractors willing to bid the job.
Okay. Did the bid documents include a site for the casting segments, or did the contractor have to find that on his own?
The contractor identified the site on his own. We did not provide a site in the bid documents.
Okay. We'll go on into the construction questions that came on. And I guess the first question we had was, the construction of the bridge is considered to be very difficult.
Yeah, this is Bernie Sincavage. I was a project engineer for LaDOTD on the project here. Our team had not been involved in this type of project before, so there was a learning curve that we had to go through. But after the first few segments, we were able to get into the mode of how the operation, how things need to be constructed. So after that, things went pretty smoothly for us. We had more challenges with the substructure basically than we did with the superstructure.
Okay. There was a question about did LaDOTD have sufficient qualified bidders for this project, since the superstructure type was the first?
So this is Paul Vaught. That was a concern for us, and part of the reason why we had the bid alternative. We knew that we had built steel trapezoidal boxes in the past, and we knew that we'd have bidders on that part of the project. So we were actually concerned as to whether or not we'd even get a bid on the segmental, but as it turned out, we had 3 qualified bidders bid on the segmental option and only 1 bid on the steel trapezoidal box option.
Okay. There was a question about the Falsework Tower. Was it on its own foundation? The picture showed it being on the foundation that you built, but was that in the original design, or was that was the foundation made bigger to provide that?
No, the original designs assumed that towers would set over the front row of the piles or the drill shafts. PCL had finished a project and their towers were a little bit narrower, so it sat a little closer to the pier, a foot and a half, couple feet, but it was basically the concept shown in the construction sequence drawings in the contract documents.
Okay. Was the tower relatively easy to remove from under the completed structures?
Yes, it was. They had jacks on it. They had jacks underneath it, and so they were able to jack down the tower.
Okay. Okay, we had some questions about the geometry control of the segments for assembly with all the curvature and everything. You want to comment on that?
The contractor used a program called MC3D to check the geometry control. As you can see in one of the pictures there, we had the three surveying stations set up on the area where the resteel was tied. And they used that to check the segments after they were before and after they were poured.
Okay. What were some of the special considerations given to post-tensioning the curb segments of the bridges?
In the design, we took a look at what the what the tendon forces were for the radial forces on it, and the blocks and deviation points were designed accordingly. So it was considered in the design, and the forces included in the segment detail design. Okay.
Were the segments basically little tangent sections? What did you do? Vary the overhang or something to get the curvature?
No. Well, the segments are trapezoidal. So if you think about it, it's a series of little trapezoids that go around the curve. The pier segments were rectangular.
Okay. Did you have to do any changes during the installation of the precast bridge segments at all? Did you run into any problems along that line?
No, not really.
Okay. All right. There was a question that came up about the post-tensioning, whether it was, this was before the presentation, about whether it was internally or externally, and then bonded or unbonded. And you kind of answered that. You had a little bit of both. And it said, if unbonded, though, what type of filler has been used?
The positive moment and continuity tendons are unbonded, but they're unbonded because the ducts run through the deviators and the pier segments. They were all grouted. The tendons were all grouted. Whether they were.
Yeah. Oh, that's fine. There was a question about, do the external tendons sag with the weight of the grout?
No, they're pulled pretty tight.
Okay. There was a question that came up about, I think before the presentation. It said, what is the purpose of the casting machine core? You showed on slide 7, I think you showed the thing of the casting yard. But the casting core, go ahead and explain that real quick.
Well, the core of the machines, what it does is forms the inside of the segments. So it's retractable. It comes in and forms the inside. So the inside faces of the web and the top slab, and it's formwork basically.
Okay, let's get another question on the tendons. About the tendon, were non-symmetric tendon layouts at all considered to counteract the torsion due to the tight radii? You have more tendons on the outside versus the inside? No,
it wasn't an issue. We didn't do that. It wasn't really an issue for what the capacities of the webs were, and the continuity PT gave us some advantages for the shear and things. And as normal practice, we typically don't do that just because of an unsymmetrical tendon layout can cause you restrictions in the future should something change, like striping of the lanes or some other things. So that's not a normal process.
Okay. Yeah, that's fine. There was a question beforehand about precast concrete barriers used on the project. The picture showed rebar. I guess you formed the barriers at the end after the bridge was done. Is that correct?
Yeah, the precast barriers were used to close off the ramps that are scheduled for future construction, specifically the WS, ES, the remainder of I-49.
Okay. On the bridges, did you slip form them though at the end? Is that what you did for your barrier?
The bridges were all slip formed.
Yeah. Okay. One final question here was, let's see. Oh, there's a couple more. Is the top slab of the segments the riding surface, or is there an overlay?
No, that's the riding surface.
Okay. Did they have to grind it or anything?
The ground, and that was a very good way to go. I think all the bridges in Louisiana should be ground like that. It's a very smooth riding surface, smoothest I've ever ridden on a bridge.
Okay. Okay.
Another advantage, Paul. Another advantage of that is you get a higher quality product since you've cast it in the casting machines than if you apply a secondary or a wearing course on top of it. So
okay.
In areas that don't salt, that's the preferred method.
Okay. There was a question. The pictures. This came in during the presentation. Was epoxy-coated rebar considered for the project? It didn't look like there was epoxy-coated rebar.
No, but as policy, we don't use epoxy-coated rebar in Louisiana. We did away with that several years ago. We've essentially gone to a high-performance concrete mix with a much lower density or higher permeability.
Permeability, yeah. Okay. Then let's go over toward. Were the bearings installed? When were the bearings installed and grouted?
The bearings were on top of the piers when the segments came in. The contractor chose to grout the bearings. Bernie, you may remember. I think maybe after the third segment pairs were up, the design was based.
The third one was up. Yes, correct.
And the design was based on grouting them at the end of the cantilever or at the end of cantilever construction, just to have the ability to maybe do any geometrical adjustments. But I think it worked well. I think it worked well locking the bearings or grouting them in after the third pair.
Yes.
Okay. All right. What is the design life of the bridge based on the concrete mix that was used?
I'd heard 150 years.
Okay, that's great. That's our maintenance question. We have a few on cost. I'd like to get to those. What was the cost per square foot for constructing the segmental bridges?
That's a hard thing to really weed out, but the best we can tell in breaking out the bridge quantity items, it was about $275 a square foot.
Okay. There was a question about the break-even deck square footage to go segmental, considering cost of the casting beds. Craig may have a handle on that. I don't know.
With this was, even though the contractor had multiple machines, it was one design. So if you had enough time, you could have cast this project with one machine. But to meet the schedule and things, they went with 3.
Okay.
So,
well, actually, Craig had 5 out there.
Oh, that's right. That's right. You're right, Bernie.
5 machines. They started with 4, and then they added another one after a few months into the job.
Okay. And then one final question on cost. It was about how did it compare the construction contract cost? The bid cost, I guess, versus the engineer's estimate.
The low bid came in slightly higher than the engineer's estimate. The low bid was $137.8 million, and the engineer's estimate was $129.4 million.
Okay. That's good. Mary Lou, it's about 10 after. Can we turn it over to you, and you have any questions you want to pick up?
Okay, thanks, Paul. There have been quite a few questions that have come in. We'll have those posted in the archive, but I'll ask a couple more quick ones. So one of the questions is, can this bridge really be called ABC construction? And I'll start with that. Precast segmental is considered one of the ABC tools. For example, the segments are constructed off-site and quickly erected on-site. So yes, it is an ABC tool. Would the speakers like to say anything on that? Anything further?
I'll just say that the overall construction time for the project, I think, was 835 days, which was almost a year less than what the max allowed days were. This was an A+B bid project. There was a lot of other site work that had to take place to build this structure. And like Bernie alluded to, I think actually erecting the segments was probably the fastest part of the overall process.
Okay, thank you. Yeah, and ABC goes from planning through construction, so it's not just the segments, although the segments are precast, segmental in this case. Another question, any particular seismic consideration?
No, it was a low seismic loading area.
Okay, and just one final question, we're out of time, I think. Is the Louisiana DOTD considering use of segmental in the future?
I'll say yes. It's something that this project was overall successful. It had its challenges like any project would, but at the end of the day, I think we ended up with a really good project, and certainly when the opportunity for a similar type project presents itself in the future, segmental is something we'll definitely be considering.
Okay, thank you very much, and Atura, we'll turn it back over to you now.
All right, okay. There's one question that I would like to ask maybe, and we'll wrap the webinar. Did you incorporate any technology to make it easier for maintenance purposes for inspection of the grouted ducts in the future?
With it, the ducts are not bonded for the continuity or the positive moment. They're in PE pipes, so they're easy to check. Easy to check on if there's any grouting issues or any corrosion. At some point in the future, if a duct wanted to be replaced, I don't want to say it's easy to take a duct out, but it's possible versus, you know, a lot of bonded post-tensioning. It's virtually impossible to remove them. So that was built into it. Also, there's capacity to increase the post-tensioning in the future, was built into it too.
All right, thank you. Thank you for excellent presentation. So on that note, we will end the webinar, and we hope to have our audiences join us for our next webinar. Thank you.